We will code and train Qwen 3 large language model from scratch, and you will understand all of it, the entire architecture and code and logic intuition behind it. Step by step, everything is explained. And there are some animations that I will show you that will make it easier for you to understand. So we have this prompt interactive mode. Today I will have a walk and let's see what it generated. So there is a bit of coherence. I just trained it for 15 minutes on Google Colab free GPU, so that's not enough compute. But if you train this for a few hours, or if you use better GPUs, then it will be a lot better. Today I will have a walk and discuss the following strict rules of the following command. Number 1, IK contra affair happened during the law rather than anything else. I think if you let this train for a few more hours, it will actually make a lot more sense. This was just trained quickly for a few minutes. So if you look at Qwen technical report, you can see its architecture, and you can also find architecture in the transformers library of Hugging Face. So this is going to be the most advanced transformer, plus all of the things and specifics that Qwen specifically has. For example, grouped query attention and SwiGLU activation for the feed-forward layers. One thing I will also add is Muon optimizer for 2D matrices. I didn't see this in technical report, but this is the new best optimizer. It trains better, it trains faster, and I expect this to be in the next iterations of Qwen, because everybody will start using this. So let's scroll down. So I will be focusing on Qwen specific things. If you are not 100% comfortable with basic attention mechanism or tokenizers, then I recommend you watch this course. If you go ahead and click here and click here, then you can go here in the beginning, and then I'm gonna be explaining both tokenizers and attention mechanism 100% visually with these numbers, with these vectors, so you will understand everything here. You see, everything is 100% visual, everything. I've been making this video for a long time to explain it well, and the code as well. But you can even watch this entire course, because it's very well explained. We will use the entire thing in our Qwen. So by understanding this, you will understand almost everything that we will do in Qwen, because language models are very similar. But this course is definitely more beginner friendly. You can also go below and click this Andrei Karpathy. So this is very famous course. You can watch this if you want. Some people find it a bit dense. I recommend you watch my course first, because I think it's more beginner friendly. And then you can watch this as well. It's very good, but you will need some time to understand it. But you can also just watch this course after you watch my course, so you can watch all three. So we will use a GPU, and we can start with the imports. So I'm gonna use a GPU, and I'm gonna just run these imports. You can go here and change runtime type and select this GPU. Just one little warning I have. This notebook will ask you for Hugging Face token. Maybe you can just press cancel if it asks you, because you don't need it. So I commented all of the imports. For example, what's important is this one is important. So this will automatically change precision of your variables, of your data in the memory. Now this GPU is a bit older, so it only supports float 16. There is no BF16, but this will work well in this GPU or other GPUs, even newer ones. So you can read this if you want, but I will skip to the next one. So we will set random seed. So we want to control randomness of torch, of CUDA. So when we have different training runs, if we want to compare different training runs, different architectures, we don't want randomness to influence. Although there will be some randomness that comes from GPU hardware, which is impossible, or I don't know, very difficult or impossible to fix, but it's very minimal and it's okay, it doesn't matter. So below we will go on to model configuration. Here I would expect you to understand basic terms, attention mechanisms, so you can go and watch these other courses, because I will try to explain this as well. Inner dimension of the model, this is the token embedding vector dimension, number of heads in the self-attention mechanism, number of decoding layers. I will be using these technical terms, and if you don't understand them, I recommend you watch those tutorials courses that I explained, or you can just search on YouTube for self-attention mechanism. There is infinite courses. Number of decoder layers. So one layer is attention and feed forward, and then again second layer attention, feed forward, so they just stuck. And this is the inner dimension of the feed forward network, and it should be 3 times this guy, model embedding, or no, 4 times. Usually it's 4 times, but can be different sizes, not just 4 times. I can show you here. So decoder only transformer is only this one, and you can disregard this middle multi-head cross attention. So we just have this masked multi-head attention and feed forward, and that's one layer, and then you stack them onto each other. In the end, we have, after everything, all of the layers, we have linear and softmax. So this feed forward layer is actually this feed forward here. And so you got here, you got expansion, and then you got to this 4 times, and then you got contraction back to exit the feed forward layer. Batch size is 24. This is just a bit lower for this Google Colab free GPU. And then maximum steps, 5. This is very low. I was just testing if my whole network, whole setup works. So you can just put this to 50. But if you want this to maybe learn a little bit, we can put to 2000 maybe. This will take maybe 2 minutes or 1 minute on this GPU. Of course, the time it takes will depend on the model size, not just number of steps. So bigger model will take longer for every step. So once you want to seriously train it, you can add maybe 2 zeros here. Now this would train for too long on Google Colab because this GPU is T4, very old. But if you have newer GPU, and also I think 20,000 will also be good generation, but even 2,000 will be good, somewhat legible. It will make some sense, the text will make some sense, so we will just keep it like this, maybe for faster training, and maybe to test it, maybe later we can increase. But for this tutorial, just 2000, it will take 3-4 minutes to train. Now a bit of Qwen 3 specific parameters. So there is 8 heads, but there is just 4 key and value heads. So so 2 query heads, because this is just 8 queries. So 2 query heads will share 1 key and value head. This is for faster computation. And they figured out a long time ago that we don't need 8 key and value heads, we can share some. So during the computation, these 4 key and value heads will be duplicated or repeated. So to match the number of query heads, 8. So they will be like this, key head A, repeated. And then first 2 query heads will have its own key head. And then key head B, etc. So it will just get repeated like this. So query head 1 and query head 2, they are different, but they attend to same key head A and value head A. Both of them are just repeated. This is gonna reduce KV cache memory massively by half. So when we have sequence of tokens, we are calculating KV, key and value heads for every token, and we are saving it. But for the last token, we are calculating query, and we are not saving query for other tokens, just for the last. So we use that query to check against all of the other keys and then get the values. So we need to save values and keys of every other token in this cache. So we will reduce all of this memory by half here. So Qwen can also have this sliding window attention. This is for very long sequences. So you can have full attention for the entire sequence in one layer, one transformer layer. And then in the next layer, you just have last 4,000 tokens. And the next layer you use full, and then, so that's one way to do it. But in this case, we will just put larger value than our actual sequence length, which will just disable it. Because we don't need, this will require, I think, more compute, and it's not necessary because we have very small sequence length, but you can look into this if you want. To implement this, you can just use this command from Hugging Face Transformers, create sliding window causal mask. So you can just do it quickly and easily. And these functions are very well usually implemented. They have custom kernels, they're very fast. It's something that like best engineers implemented, and they are very fast. So I recommend you using PyTorch functions or Hugging Face functions instead of coding your own, unless you know like exactly how to make it fast and good, or you know some trick to make it faster. Attention bias. So when you are initializing these query key value linear layers, you can actually have bias there as well. To the best of my understanding, they are not used in most cases in original transformer, but I've heard some people saying like some specific things, maybe in pre-training it helps, but then you disable it later, but I'm not sure about this. So I will keep it false. If anybody knows, you can comment below. Maybe the new OpenAI open source model GPT OSS used attention bias, but I'm not sure. And then this small RMS norm epsilon, it's a very small number, just so we can later prevent division with 0. I think we can speed up now. So gradient accumulation steps, this is just, instead of processing one batch and then updating gradients, updating weights, I should say, you process this 4 times the batch, you accumulate all of the gradients, all of the weight changes, you add them, and then you update the weights. This is gonna simulate larger batch size, but in my experiments, it's better if you can crank up the batch size, it's faster. And but if not, if your GPU is too small or not enough memory, then you can just simulate larger batch size by just processing this batch 4 times and then adding all of the gradients. Muon optimizer learning rate, so we need a bit higher learning rate. It's good. This will actually make it learn faster because Muon is good at fast learning. It already solves problems with some unstable big numbers, and it orthonormalizes update matrices. I'll talk about that maybe a bit later. Maximum number of tokens we have. If you have better GPU, you can increase this. So if you increase this, that's maybe the best thing that will improve your training. You want to increase maximum sequence length, but you also want to increase batch size. Okay, so you want to keep max sequence length probably at the powers of 2. And you want to keep all of these numbers at the powers of 2 if you can. These are not right now because the GPU is small, but if you can, you should. And also know that as you make these powers of 2, as you increase, your memory will increase exponentially. So even 2040, this would be like too much. And then you can look at how many batches at the same time and what's the sequence length. You can reduce these 2 parameters if you don't have memory. And if you cannot double this, then you can increase batch size a little bit. I think usually when you decide on the architecture, the best improvement to training you can do is by increasing maximum sequence length most of the time, but it's more complex and nuanced than that. But anyways, we will return this to 512, and you want to get this up and get batch size up until you fill the memory. So you don't want to just have GPU and wasted memory. So it's difficult to calculate or to know how much memory this will take in advance. So you just load this, you start the training, you check the memory, and then you increase these parameters until you fill the memory. And then these are kinda not so important. Starting from here, this is how many documents we download from data. You can increase this, but this is already a lot of documents downloading, so you don't need to worry. Only if you are gonna increase steps, number of steps, wherever that was, by a lot, then you maybe want to look into downloading more documents. but you can also ask AI. I'm gonna leave this whole code in the Python, like you will have it in one Python file, so you can copy all of the code. You can just run that Python, it will also do everything. You don't need to change anything. And you can use cursor or ask AI to help you with more data and explain this. This is evaluation. You can increase this if you don't want to see so many evaluations so often, but I'm training for only a few steps, so I want to have these evaluations just to check the training progress, but you don't need to evaluate so often. Okay. And then weight decay is just punishing large weights, so we don't want weights to be large. We want weights to be maybe between 0 and 1 or up to 10 maybe, but that's also a bit large, because if we have large weight, then small input change will have huge impact, because you are multiplying weight by input. So if you have a huge number multiplying, you don't want that. You don't want like single weight to carry so much importance. You want a bunch of different weights to carry equal amount of importance or less or more similar amount. And then neural network can learn different patterns and stuff. Dropout and gradient clipping, this is just for regularization to make the training not overfit onto some data. And let's look at this. We just need to have the model dimension be divisible by the number of heads, and number of heads divisible by number of KV heads, and all this good stuff. Now this is the function that's gonna repeat key and value heads. So as I said, you have 4, and then the first key value head will get repeated 2 times, because we have 8 query heads. So first query and second query head will get the same key value head but repeated. So you can multiply. You have now 8 of both. I added some comments here. So if we have these 4 dimensions, this is sequence length, by the way. So we have batch, number of key value heads, sequence length, and head dimension. Okay. And then if we add this none here, this will inject 1 in dimensions. So this will create a dimension. And then we can just use that to replace that number with the number of repeated repetitions. So in this case 2, because we have 8 of these and 4 of these, so we need to repeat the 4 2 times. And then we can multiply here to repeat. Here I have some optional exercises for you to understand this. So this is not necessary for the language model, it's just some tasks that if you want, you can run this, or you can copy these cells into ChatGPT and ask it to help you to explain to you. You can use new study mode by ChatGPT, it's very good. Okay, now we go to the Muon optimizer. Okay, so this is gonna be tough to understand. This is pure mathematics, but I'll try my best to explain. Actually, you can check my channel and you can search for Muon optimizer. There is a bunch of videos here. So here, Muon and Muon, and there is like 3-4 more videos. So when you have weights, these are neural network weights, okay, and then you do the backpropagation, and then you get what's called update matrix. So update matrix just gets subtracted from weights. So each number, if this matrix gets subtracted from each number here, element wise. And the goal of this is to change weights so the loss is smaller, loss goes down, so the error of the neural network goes down. So this is how neural network learns, by updating weights, making weights better. But we have some issues with this raw update matrix that gets subtracted. So some of the numbers there could be arbitrarily high, not because those high numbers would reduce loss better, but simply because those numbers are getting multiplied by some arbitrarily randomly large input number. Because remember, you are multiplying inputs times weights to get some output. Okay, so when you are calculating gradient, you are calculating how much this particular weight is changing the output. But this particular weight might be changing the output a lot just because some input number is arbitrarily large. For example, if you have cats, dogs, and fish, so you assign number 1 to cats, number 2 to dogs, and number 10,000 to fish. Number 10,000 multiplied by some weight will have huge influence. So this weight will have huge influence onto the output, just because this randomly assigned 10,000 number, 1 to 10,000. So when we go with the back propagation, we see that this weight has a lot larger update and strength than the other weights. So we actually want to normalize that, we want to squish that, we want to prevent that. So this is what Newton-Schultz will do, what Muon optimizer will do. And I recommend you watch this back propagation from scratch, so it will explain this, it will help you a lot. So I put the link here above this cell, but I can show you this. So when you are multiplying some input vectors or numbers or vectors with weights, it does a linear transformation. You are multiplying a matrix with a matrix. So let's say these are input weights, these arrows. You see how multiplying with a matrix, it will stretch, rotate, reflect, it will do everything. So what we want to do is we want to prevent this stretching, because this stretching will happen when some weight is huge. So we just want to have rotating vectors, not stretching. Because what happens often, well, is getting complex. This is from the tutorial backpropagation from scratch, but I will explain. So sometimes stretching is good for reducing loss. So sometimes stretching is good, but the way I understand Muon is they figured out that most of the time stretching is happening not for good reasons, for loss reduction reasons, but just because these input numbers are arbitrarily high. That's my understanding. So it's better to remove stretching altogether, even if stretching in some cases will improve loss. It does a lot more damage. So they are transforming matrices just to rotate and not to stretch. That's a Muon optimizer to the best of my understanding. It is a bit complex mathematical concept, and in the future videos I will understand it even better and have better animations and ways of explaining it. You can also watch this video, orthonormal matrix, because orthonormal matrix is one that's gonna, orthogonal matrix is one that's gonna rotate the vectors, and normal matrix has this norm, the length, the magnitude when you square and sum and root all of the elements close to 1. So if you don't understand, orthonormal matrix will just rotate vectors, that's it. And that's what Muon does, just rotating instead of stretching. So I'll leave a URL to this video as well. So this is what orthonormal matrix will do in this other tutorial. You see, it just rotates, it doesn't squish or stretch. So how do we know matrix will just rotate? It's when we look at the rows of a matrix separately, or columns, but in this case rows. And each row, if we plot row as a vector, then all of the rows, all of the vectors will be normal to each other. So 90 degrees, 90 degrees between every row. So that matrix will just rotate. So that's orthogonal matrix. I will be making more tutorials, and you can check more tutorials on this, and I will be explaining this even better in next courses when I figure out like how to explain it better and how to have more animation tools and stuff. So what is this Newton-Schultz? So imagine you have any matrix and you have some function that's gonna transform this any matrix into orthogonal matrix. So it will just look at each row and make them normal to each other. So it's a function that transforms any matrix to orthogonal matrix. But this theoretical function, there are a few different ways to do it, but each of the ways is too computationally complex. So, you know, this function, as well as many other functions, or maybe even every function, I'm not sure, can be approximated by a polynomial. So polynomial is just, you have x squared plus x plus 3, or x cubed plus x squared. So it's just squaring that is multiplying and plus, instead of having complex root, inverse, computationally complex functions. So whatever this theoretical function is, we can approximate it with polynomial. So this is the polynomial that we are approximating, this theoretical function that's gonna take any matrix and orthogonalize it. So this is, first we calculate this x times x transposed, and then we have, so we get this a. And so we have a squared, a, and then without any a. So this is the polynomial, if you look at this carefully. I'm still trying to understand this part. I'm still trying to get intuition behind this, and a lot of videos are about this on my channel. So in the next courses, I will understand this better. But this will not immediately transform this matrix into orthogonal. It will just move it a bit closer to orthogonal. So you need to put this matrix 5 times, apply this function 5 times. Every time it will be a bit more orthogonal, or 10 times. So usually 5 to 10 times is orthogonal enough. Neural network doesn't need 100% perfect things usually, 100% perfect weights or initialization or matrices, but close enough is good. So 5 times, I think we do it here, steps 5. And then that's gonna transform our matrix into orthogonal and orthonormal, because we have normalization later as well. Then we have this class defined Muon optimizer. So we will just have some learning rate. This is high learning. This is very good because this can handle higher learning rate and it can converge faster. So what people found is that you can train the model with 2 times less data, or almost 2 times less data. Even though you might see iterations per second maybe go a bit down, but every iteration will teach the model a lot more. So I mean steps per second when you train the model. So don't think that just because Muon optimizer has a bit slower steps per second that it's actually worse than Adam W, for example. It's actually learning more per every step than Adam W. So here it's gonna use momentum. So it's gonna use either standard momentum or this Nesterov momentum. It's gonna calculate the update orthogonalized matrix here and then update the weights using the momentum as well. And this is just some transformations depending on the weights of the shape of the weights matrix. So it applies the update properly. You can copy this line of code and ask ChatGPT Learn to teach you step by step. We will not focus on this right now because it's simple for ChatGPT to teach you this. And it's good for those viewers who want to understand this better. So you can just see the shapes. This is left to the viewer as exercise, let's say. Then we have data loading. It's very simple. So we will use already done tokenizer. Tokenizers, it's not so important. I don't want to focus on that. You can watch my course that I show to you. It's simple. You will understand everything there. And we will train and build tokenizer there as well. So we will use this tokenizer and this data. It's small LM corpus by Hugging Face. This data set is very good for training small language models. It's very clean, it's simple, and tokenizer is not too big. It's perfect for small language models. So we will just load this data set and this part of the data set, and we will use this tokenizer. And we don't want to load all at once because there is too much, so we will just load number of documents determined by our hyperparameters that I explained above. When it asks you for this Hugging Face token, you can just press cancel. You don't need to give that. These datasets are public, so you don't need that. So this part will just process the dataset, the corpus. So dataset is saved in these documents. So document is just some JSON file. It has text, it has metadata, it has title, it has a bunch of this stuff. So we just want to extract text from each document and then append all of the texts. And so train on that big text, our model. So our model will just see whole text combined of every document. And here I'm not appending more than 3000 characters of every document, maybe to keep the diversity up, because we're just gonna train this for a bit. And so we have some printing logging, just showing how many tokens we have and stuff. So, and that's it, that's prepared dataset. Then we have this dataset class that will manage this downloaded data, downloaded text, and prepare it for training. So we just create, if we have all of the text, we create some window, sliding window. So we are putting this into the model, and then this it's like moving like this. So what we are putting into the model. This is the code, it's very small. I recommend you copy these things into ChatGPT Learn and just ask it for some examples and maybe ask it for some exercises, because again, coding is something you just need to get intuition for by playing with it a little bit. So I will leave this ChatGPT conversation that will explain this to you. So it's this one. We have, let's say, some tokens. These are like some words, each of them. And then sequence length of 4 tokens. So length of data set, it's going to be length of tokens minus sequence length, which is 3. So this is the input. And then this is the output, for each token is predicting the next token. Okay, so you have these first 2 tokens, you predict this one. You have these tokens, you predict this one. You have these, you predict this one. So, and then you can use the same thing, just move by 1, and you can use the same thing again. So that's how you get X and Y. X sequence, and then Y is just shifted by 1 every X. Then we go on to ROPE, rotary positional embeddings. So when we have sequence of tokens, how does neural network know, the LLM know, which token is at which position? Well, we pass every key and every query of each token through this forward of rope. So again, this is again rotating vector and rotating matrix that's gonna rotate that vector. That vector meaning like the key and query vectors. And then neural network will learn based on the rotation that I showed you earlier, the animation, where this token is in the sequence. And also it will learn, for example, that 100th token will be far away from the 10th token, but close to 95th token. I will leave this link below. So this is what rope looks like. So we have position 0 to 512, for example, in this case. And you see how we use sine. This is cosine actually. And we have sine as well. So we use both of the components. Half of the rope vector is going to be cosine transformation, cosine values, and half will be sine. So you see the difference. Every position has its own type of like values. So position 0 has a lot of values at 1. So these are, by the way, these are embedding dimensions going from 0 to 30, 32 something maybe. So a lot of the positions are at have value 1, but as we go down, you see that higher dimensions get lower values as we go like further in the sequence length. So what I'm trying to say is that every position has its own hard-coded vector. So this is hard-coded. This is not learned by network. But network will see that this vector will rotate key and query vectors, and it will know based on rotation which position rotated it, so which position that key and query belong to. You can just watch first part of this video that explains this. It's maybe 4 minutes or a bit more. I recommend you first watch this video. I actually have a good explanation here of how rope works. I drew everything. So I will leave the URLs here. So this one is the first video, the theory that you should watch. You can watch beginning part of this video and this video as well. First, it defines these frequencies. As I showed you the picture, the sine and cosine wave frequencies become larger and larger as you go to the right. The sine waves become huge, and in the beginning they are very small. And it will split your embedding, be it query or key, into two parts, two equal parts, and then apply cosine to the first part rotation and then sine to the second part. So this is entire rotation matrix. So then it will again apply minus sine and cosine again to the same parts, and then it will concatenate y1 and y2. So this is just rotation matrix that will rotate your vectors. This rotation is same as when I was showing to you in the Muon optimizer, works in the same way. It's just rotating all of the vectors. So depending on how much it rotates, the LLM will know the position this is in, because the sine and cosine will be different as you go down the positions. They will have different values. Check this ChatGPT URL for interactive one-on-one coaching by ChatGPT, and you can turn on the learning mode, or you can just copy this and tell it to teach you one-on-one interactively. Then we go on to the self-attention mechanism, the grouped query attention mechanism. So this is where the rope will be applied, by the way. Here we are defining the rope here. And we are applying or putting query and key through our rope to rotate them. But let's go back and look at this again. So as I said, I recommend you watch my course on Llama 4. This has very good explanation of self-attention mechanism, and you will understand the basics and mathematics and visualization completely. So then after you understand that, this will be quite simple, I must say. Although if you see self-attention for the first time, it will take a few weeks. It took me some time to understand it. Just try practicing it. Try drawing it, try explaining it, try understanding it. And you can try to explain the same way I explained in that course, all of the numbers and all of the drawings. Very simple. So we just define these variables that I was explaining in the beginning of the video. And then we create these projection matrices. So this will take our token embedding and project, multiply with some weights, convert it to the key. Multiply with same embedding with different weights, convert to query and value. So each of these will take the model dimension, so the vector, the token embedding, and project this into the key query value vector. And this is interesting. So the dimension of this vector is going to be a number of heads, so number of query heads times dimension for the query head. So they are using key because I guess dimension is same for query, key, and value. For each head, dimension is same, so you can just use one parameter. So, and that's it. So what this linear layer will produce is the whole long embedding that contains all of the heads. And then in this self-attention mechanism, all of the heads will be split. And then all of the heads will interact with each other separately. So the first head from query with the first head of key and value. As I said, this attention bias usually not used, but maybe there is like some tricks to use it in some layers of training. I'm not sure exactly. Maybe in the future I will understand this better and tell you. Then we normalize all of the heads with RMS norm. RMS norm is very simple to understand. I recommend you ask just ChatGPT learn mode to explain. It's very simple. So for every dimension in the vector, you square that dimension. Then you sum up all of the squares. And then you divide the sum of the squares. So here you get, you divide sum of the squares by the number of squares. Okay, intuitively, what you get here is average square value. So you get average square value of dimensions. And then you root. And now you get average dimension magnitude. So this is the RMS normalization. So that's the root mean square. But to normalize, to apply the normalization, you divide every dimension with this average magnitude of the dimension to normalize it. So you can continue the conversation with ChatGPT if you want. And enable learn mode, because I cannot share learn mode, so you need to enable it manually. I'm gonna give this URL here, practice RMS norm one-on-one with ChatGPT. Here we will also define rotary and dropout. So the forward method of this self-attention mechanism, we get these query key value project matrices matrices. So there are some tricks. You can combine all of this into a single computation. So instead of having 3 linear layers, you just concatenate. You put one linear, second, third, you just put it into one big layer, big vector, or big matrix, I should say. And then apply that to X and then split. This part is for key, this part for this part for query, key, and value, just split later. But you can do it separately like this as well. DeepSeek combines it, a lot of people combine it, but I think in Qwen it was separate. Then you separate every head, and then you apply the normalization. This is our RMS norm. And then we apply rotary embeddings, but see here, we put head dimension first, and then sequence length and dimension of each head after, because we just want to completely separate every head. So we don't want to have sequence length and then grouped like by tokens. We want to have grouped by different heads. So for each token, we just have key, query, and value of this particular head. I recommend you copy this into ChatGPT and ask it to give you some examples or exercises if you don't understand this. I'm telling you this because there is so much details here, and this course would be 10 hours, and it would be confusing for people who already know this. So I'm trying to make this course fit for everybody. And you can get one-on-one learning from ChatGPT. That's how I learned this. So that's the best way for these one-on-one learnings. Hello, it's me from the future. So I removed these transposes here, but we actually need to have them. So that was a mistake. So just if you are wondering why this is going to look a bit different in the video for some time. Because I thought we are already transposing it here, but we are not. We are just permuting these dimensions, but we don't save this transpose into this query and key. So we need to actually transpose them again. I thought I was transposing 2 times, but then I wasn't actually, so I needed to fix it. And then we repeat query key heads, and then we just apply the attention. And this is very good, very fast attention by PyTorch. Usually you want to use these functions by PyTorch. They're very optimized, very fast. It will be faster than if you code this yourself, unless you are expert or you are coding something completely different. And in the end, we just want to transform our whatever output is from attention into the vector embedding back. So this is how we finished the attention mechanism, attention transformation. So then we have this feed-forward network. This is a classic feed-forward. So we have up projection from model dimension, from token dimension, to the expanding 4 times bigger inner hidden dimension, and then down projection from this 4 times bigger back to the model dimension. So this happens after attention layer. Output of attention goes into this. So we just project up. This huge hidden layer has a lot of neurons that will hold some information and hold information on how to process output of attention, how to mix it up to get some useful information. But the thing with SwiGLU is we also have this gate. So it's same thing as up projection. I mean same transformation. So this gate will just activate and deactivate some of the neurons in this big hidden layer. So this gate will be passed through SwiGLU, and this is SwiGLU, the pink one. So you see that if the value of input is larger than 0, then the SwiGLU will return almost same value. But if the value is smaller than 0, then SwiGLU will return some value very close to 0. So we will basically have this as on and off switches. So some neurons that are larger than 1, they will remain that are larger than 0. And lower neurons will become almost 0. You just look at the pink, ignore the blue one, that's ReLU. So then we multiply the output of the SwiGLU with the output of the up projection matrix. So with these neurons, the hidden layer neurons, and for all of the neurons that get multiplied with values that are close to 0, they will get deactivated, or they will get reduced or suppressed. And other neurons will be just multiplied with these other gate numbers, that they will not get suppressed, or they might get amplified. So this is additional level of control. This can learn to suppress and amplify these inner neurons based on the X input. So instead of always processing the neurons in the same way, we have some amplification and reduction. So you can think of this gate times value as brightness control times light source. Light source being this with this up projection, which is source of information, and then brightness control is to amplify or to suppress it. And then transformer block. So we will just define all of our things. I can show you the forward method, defining attention. So we have input, we normalize input, we pass through attention. And then we have some dropout. I think we don't have it in this case, we just set it at 0. But we also have this residual connection. So we are adding the input to the transformed attention. So this will keep some initial information. And then pass through norm and neural, this feed forward, and then residual connection, and that's our transformer block. So you see here we have multi-head attention, but norm is before. And here feed forward, but norm is before. So it works better. And then we have complete language model. So starting from defining the token embeddings, which is vocab size. So for each token we have the token embedding, so it's the model dimension. Position dropout, I think we are not using any of, we are just setting it to 0. And then list of these transformer blocks, which is equal to our number of layers, which was 6, if I remember correctly. Normalization, output dropout. And then we tie input weights to the output weights. So we have this output head that's gonna take token embedding and project it into the whole vocabulary size. So it will create probability for every token in the vocabulary to be the next token based on this, whatever got processed here, the output of the processing of the transformer. So it's this linear layer here. Now it will not give probabilities, it will just give logits, numbers. And then we will convert those logits into probabilities, as I explained in the softmax. But you can have same weights of this layer and the input embedding tokens layer. It will work same, and we can reduce memory and it will work well. This example will illustrate better. So in the beginning we have this lookup table. So first token has this vector embedding, second token has this vector embedding. Actually, you can take this entire matrix and use this as weights in the final linear layer. So you can use that to multiply the output of the transformer with the entire lookup table to give a vector that's vocab size length. So this example will illustrate let's say we have this lookup table. So this is in the beginning. Every token has its own vector embedding, token 1, token 2. And then after the processing of the transformer, in the end, we get this vector. So this should also represent some kind of token. But this may not be any specific token in the lookup table. It's just some info vector. So in the final output, how we multiply this vector with this, we get some number. So it's dot product. We get some number. And then this with the next one, we get some number. Dot product. So if we have some token that's very close to this, the dot product will be very, very close to 1, very big. So then for every multiplication, we will get some number, and then we can apply softmax to find the probabilities. So the resulting vector will be a length of vector, so number of tokens. And that's how we can use same weights to save on memory. I will leave this ChatGPT chat here if you want to check it yourself. Below that, we have the way of initializing weights. So there are some different, better ways to initialize weights than just random initialization, or you can use random or any of the ways. And then forward for the transformer goes like this. You first convert input into these token embeddings, and then you normalize it with square root of the model dimension. You pass that through the transformer blocks. In the end, normalize and get the logits. So that's the LLM. We can then apply softmax after. So during training, we need to evaluate model's performance. We don't need to worry too much about this. This is just gonna calculate average loss, accuracy, and perplexity or confusion. So we have our logits, and then we can calculate the difference. So we can use Y to see which tokens are correct next tokens. And then we can calculate the loss, the difference between the correct next token and what our LLM predicted. I just added some comments to help you, and you can copy this into AI and do some exercising on learning. And we can go below, and this is just gonna set up Muon and Adam W, because Muon optimizer is just for 2D matrices. So number of dimensions, if it's 2 and it's not token embeddings, it's not norm, then it's gonna be handled by Muon optimizer, otherwise by Adam optimizer. And you can see how many of the parameters are handled. This will just log. And then initialize both optimizers. And Adam optimizer usually needs a lot lower learning rate than Muon. So 10 times lower in this case. And finally, we have training loop, setting seed, initializing all of these good things, optimizers, learning rate, schedulers. You don't want to have constant learning rate. You want to change learning rate as the training goes. So in the beginning, learning rate is low, but it will quickly become big, and then it will slowly drop off. So as the model learns more, we don't want to adjust weights too much, because as the training progresses, model will know more and more, and we want to make learning slower and more stable. So this is the training loop. This is just initializing and running everything. So passing input through the model, getting loss, and then calculating gradients and back propagation here backward with this loss by passing in the loss, and then updating weights with optimizers. I will scroll through this. And we also have this printing or logging. And we have this evaluation that's going to happen every some amount of steps. And this will show the progress bar. Then we have a bunch of printing and saving the model in the end. So that was defining the training loop, and now we will run the training loop. So we will start with just some printing, setting seed, loading the config, just printing everything, and then just loading the data and tokenizer, and then splitting into training and validation sets. And then this is data, training loader, validation loader. So it will take this loaded text and feed it into the model. And then the train model, we just pass training loader into the model and validation loader so model can use it. And this is where the model downloads this stuff and starts the training. Wait, maybe this was not a mistake. Maybe this was not a mistake. I got an error. I'm not sure. Let's see again. It looks like it was not a mistake, so it was a bit weird. So our training will take 13 minutes. I'll just wait for it. You look at the loss here, you see it should be going down. It will be going down, especially as our learning rate is warming up, becoming bigger. It will start to rapidly go down soon. And then perplexity should go down. You see the learning rate is becoming bigger and bigger here very quickly, and accuracy should go up. And so now the learning rate is big. Now the loss should go rapidly down. You see it now, it's going very rapidly down. Loss is already 4.1. And guys, if you know how I can fix this, I don't want this to log my progress bar in every row, but just keep it in one row, you can tell me. And we need 7 more minutes to wait. And now learning rate is slowly going down. It first went up very quickly and then it's slowly going down. As we train more, we don't want to update weights too much as we train, as it learns more. Here we have validation, and this is checking on different data than the testing data, than the training data. But all of the data is always different because it's just gonna see training data once. So anyways, this validation loss is very similar to the training loss. It's a bit lower even. It's always confusing to me how validation loss can be lower, but maybe it's just randomly a bit lower. And then validation accuracy, it's even bigger than this training accuracy for some reason. Perplexity is better, it's lower. So I don't know how validation can be better than training, but now, before this finishes training, I want to show you how we inference the model. So model will be saved and best model.pt for now, but in the end, it's going to be named final model.pt. So we need to load the model here. It will load. We will initialize model everything, and then we will use it to generate text. We have a few parameters. Temperature just means if we increase the temperature, the probabilities will all get more uniform. So if this was like high token with high probability, it will get squished down, and low probabilities will get pushed up. So probabilities will be more uniform, so that generation will be more random. But if temperature is close to 0, then it will get like very different probabilities. So you want to have random things if you want to maybe generate poetry. You have higher temperature, but math and coding you have lower temperature. So there is no so much randomness. Top K, it just means we will sample from K most likely tokens. For example, 50 most likely tokens. And then top P, sample from the smallest set of tokens whose cumulative probability exceeds P. For example, the fewest number of tokens whose combined probabilities add up to at least 90%. And that's how it samples. So the way it stops sampling is if it reaches max length or end of sequence token. So I think this inference code is not so important and it's not so difficult when you understand the training. We also have this interactive inference that you can just talk to it and prompt it and it will talk back to you. So then I have a few of these prompts to show what it's gonna generate, and this function will run everything, and I'll show you. Looks like our training is complete, and now we have final model. So I will load the model. I will define all of these inference functions that are top P, top K, and temperature, and all of this cool stuff that calculates softmax of these next token logits, so gives you probabilities, and then you do some sampling. We want to just sample one token based on these here sampling methods. And I want to define interactive chat, and then I want to define this demo, and then I want to run. So the future of artificial intelligence, this is the beginning of the prompt, and then it continues. Okay, so it's a bit messy here. Engineering, and computer science and engineering. The systems allow scientists to design which can help solve complex systems. Actually, it does make some sense. It does make some sense. And then we also have some Python code that is funny. But we just trained it for 15 minutes on like very small GPU, and it already makes some sense. But it might look a bit more impressive than it is because this is a whole token. So it can just put a bunch of words here, and because whole word is a token, it can seem a bit more like like it's organized, even though like it's maybe more random. But these whole tokens as words are making it seem like it's outputting like coherent words. But I think it's still good for 15 minutes on this small GPU. So you can check the interactive mode. You can train this for a longer period of time. You can check other videos on my channel, courses. I'm making all of the videos about AI research, AI science, AI engineering, LLMs, diffusion, everything. And see you next time.